space and time to discover how the universe was born and how it created everything in our world and how eventually it will die. Everything we see around us is made of matter, atoms, and molecules. Take this car. It's a 1956 Ford Fairlane convertible. It's constructed from many different materials, like steel, rubber, and glass. Go deeper, and these materials are made up from combinations of elements like iron, silicon, chromium, and carbon. Each and every atom that makes up this car were created by our growing universe. Physicist Lawrence Krauss studies how the atoms we see on our planet have come to be here.
We really are part stardust and part Big Bang dust. Most of the atoms in our body are from the cores of stars, but some of them have been around since the earliest moments of the Big Bang. So we really are truly cosmic individuals.
Each and every atom was created over billions of years as our universe evolved.
So when we look at this car, of course, all the atoms in this car came from stellar explosions, from supernova processes, and from stellar evolution. But they were created at different times during the evolution of the universe.
To understand how the universe made all the raw material we see here on Earth, we need to take an incredible journey and travel back through space and time to the moment our universe was born. In the beginning, there was nothing. No space, no time. And then there was light. Suddenly, a tiny speck of light appears. It was infinitely hot. Inside this tiny fireball was all of space. This was literally the beginning of time. The cosmic clock was ticking. Time could flow, and space expand.
At the earliest moments of the Big Bang, if you take it back to t equals 0, everything in our universe, everything we can see, all the matter and all the energy in all of the galaxies was once contained in a region smaller than the size of a single atom today.
The idea that our universe was once tiny originated from the brilliant work of American astronomer Edwin Hubble. Back in the 1920s, most astronomers believed that everything visible in the night sky were stars, and they were part of our galaxy, the Milky Way. But Hubble wasn't convinced. He studied a swirling cloud of light called the Andromeda Nebula and showed that it was a star city, another galaxy, far outside of our own galaxy. He showed that these other galaxies were speeding away from ours, and the further away they were, the faster they seemed to be moving. The universe was expanding. And if the universe was expanding, then at some point in the past, it must have been smaller. Much smaller. And that it must have had a beginning. The idea of the Big Bang was born. Theoretical physicist David Spergel is a Big Bang expert.
The Big Bang theory is not really a theory of how the universe began. It's really a theory of how the universe evolved.
No one knows exactly what happened during the Big Bang, but scientists do know that a fraction of a second after the universe was born, this tiny, super hot fireball was already starting to expand.
We don't know how the universe began. So we start our story when the universe was a billionth of a billionth of a billionth of a billionth of a minute old. Pretty young. The universe was the size of a marble.
Less than a trillionth of a second after the Big Bang, the marble-sized universe was very unstable and underwent an enormous growth spurt.
During this period of incredibly rapid expansion, space itself was expanding faster than the speed of light.
In the same way that this hot glass ball inflates, so did the baby universe, expanding in all directions at once. And as it expanded, it cooled. A trillionth of a second after the Big Bang, the universe was small enough to fit inside the palm of your hand. A tiny fraction of a second later, it was the size of Mars. Another fraction of a second, and the baby universe had grown to 80 times the size of the Earth. A trillionth of a second after the Big Bang, and our newborn universe was still expanding. But it didn't contain matter. It was pure energy. Einstein's famous equation, E equals mc squared, showed that mass and energy are interchangeable. It gave us the knowledge to build weapons of mass destruction. It also revealed how the universe created the first matter. When a nuclear bomb explodes, a tiny amount of matter is annihilated and converted into energy. In the baby universe, the exact opposite happened. It converted pure energy into particles of matter. But there was a problem. The universe created both matter and its arch-rival antimatter, and when these two met, they obliterated each other. The infant universe was a war zone, a battle to the death between matter and antimatter. If they mutually annihilated each other, the universe would remain full of energy, with no galaxies, stars, planets, or life. Fortunately for us, there was an imbalance. For every 100 million antiparticles formed, there were 100,000,001 particles of matter.
But there was that one extra particle of matter left over in each volume, and that was enough to account for everything we see in the universe today.
This tiny imbalance led to all matter we see in the universe: galaxies, stars, planets, even convertibles, and ourselves. Astrophysicist Carlos Frank from Durham University in England explains.
We are a little bit of debris left over from the annihilation of matter and antimatter. We're the leftovers of that process. If the universe had not developed this slight asymmetry between matter and antimatter, the universe would have been completely boring. There would be no structure, there would be no galaxies, there would be no planets.
Quite what this newborn universe was like has challenged cosmologists since the Big Bang was first put forward. Now, in one of the biggest laboratories on Earth, they are able to recreate conditions that almost certainly existed an instant after the Big Bang. It's called the Relativistic Heavy Ion Collider, RHIC for short, and it's located at the Brookhaven National Laboratory on Long Island. It's like a time machine, taking us back to 10 millionths of a second after the Big Bang. Here, scientists like Todd Satogata accelerate subatomic particles close to the speed of light and then smash them into each other. The particles race around this 2.5-mile circular tunnel in opposite directions, 78,000 times a second, and then collide inside this giant detector, bigger than a 3-story house. When they smash into each other, they generate incredible heat, just like the real infant universe.
We believe the early universe was extremely hot, billions of times hotter than the center of the sun. And what you're doing when you're smashing these nuclei together is melting matter, creating matter hot enough to give us a glimpse of what the very early universe was like.
When the particles collide, they break open and throw out a shower of even smaller particles. It's a bit like discovering what cars are made of by watching them smash into each other.
You can race two cars together and smash them into each other head on. And when you do that multiple times, you start to see different patterns coming out. A tire comes out here, a radiator comes out there, and before long you can start to conclude that a race car is made up of these certain pieces.
What the scientists at Brookhaven have discovered is that within these superheated collisions, a completely new form of matter appears. And this matter contradicts the previous theories on the nature of the early universe. Because it's not a gas, it's a liquid. It was super hot, 100 million times hotter than the surface of the sun.
This liquid is perfect. It has no viscosity. In some sense, it would be the perfect motor oil, except it's 1 trillion degrees hot.